This is the sixth video in our series on topology, and today we're going to talk about the closure of a set. So let's jump right into the definition. So let's say we've got a topological space X. So that means we've got a set X and we've got a collection of open sets of X. So given any subset A of X, we define the closure of A to be the intersection of all closed sets containing A. So we could perhaps write that in this fancy way like this. So there's a couple of notations. We could say CL of A or A bar to mean the closure. And observe that this is the intersection over all closed subsets of X B, where A is a subset of B. And so that's encoding these words into a symbol. Now I'd like to point out here that I have the words closure of A in X, and that's because there's some context here. We're thinking about X as being the topological space, whereas we could have maybe some sort of subspace topology situation, as we'll see in our first result. Now I'd like to notice two observations that happen immediately. First of all, A is a subset of its closure. That's pretty clear by the definition. Furthermore, the closure of A is a closed set. Notice that here we're taking the intersection of an arbitrary collection of closed sets. That's going to give us a closed set by a previous result. And I guess I should say here that if the closure of A was not a closed set, then we didn't do a very good job naming our defining properties. Okay, so the first result that we'll look at involves the subspace topology. So let's give Y, which is a subset of X, the subspace topology. So we talked about the subspace topology in a previous video. Then we'll prove that the closure of A in Y is simply the closure of A intersected with Y. In other words, it's the closure of A in the larger space intersected with our subspace. And this proof is just a straightforward calculation. So let's denote CL sub Y of A to be the closure of A in Y. And observe, I can write it like this. So it's going to be the intersection over all B, where B is closed, so let's write here closed in Y, and A contains B. But now let's observe that we can replace that a little bit like this. So here this is going to be the intersection over all C, which are closed in X, where we replace B with C intersect Y. And that's because every closed subset in a subspace with the subspace topology can be written as a closed subset of the larger space intersected with the subspace. Now I'm not sure we proved that exact result, but that's fairly straightforward to prove. And then observe here we have A as a subset of B, but notice that we're replacing B with C intersect Y, so we've got A is a subset of C intersect Y. But now let's observe that we don't really need the C intersect Y here, because I guess we're assuming that A is a subset of Y given the fact that we're talking about the closure of A and Y. So since A is a subset of Y, we can get rid of that intersect Y thing there. But now what we can do is bring the intersection with Y outside and we'll have the following. So this is the intersection over all C, which are closed in X, where A contains C of these C sets intersected with Y. But observe that this object right here is exactly A bar, so we have A bar intersected with Y, but that's exactly what we needed. Okay, so there's another definition that goes hand in hand with the notion of a closure, and well, that's the notion of a limit point. But in order to get to the notion of a limit point, we need something called a neighborhood. So let's introduce those definitions right now. Okay, so let's start with the definition of a neighborhood. So given any X in our larger topological space, we'll say that a neighborhood of X is really just any open set U that contains X. So that's simply what a neighborhood is. Now, I'd like to prove a nice classification for a point being inside the closure of a set, and this is a little bit easier to work with than the straight definition right here. And so let's take A to be a subset of X, which is a topological space. Then X is in the closure of A if and only if every neighborhood of X intersects A. Now, we're going to in fact prove both directions of this using the contrapositive. And we're going to start with the reverse direction. So proving the contrapositive means that we'll take the opposite of this statement, or the negation of this statement, and show that implies the negation of the right-hand statement. So that would be the contrapositive of this reverse direction. Okay, so let's suppose that X is not in A bar. That's the negation of X being in A bar. Okay, but X not being in A bar means that X is in the complement of A bar in X. So that means that X is in the larger topological space set minus A bar. But let's set this equal to U and notice that this is an open set. And we know that this is an open set because it's the complement of a closed set, and that's something that we looked at a long time ago. That's in fact how we define a closed set, as the complement of an open set. But that immediately means that an open set is a complement of a closed set. Okay, great. Now let's look at the following. So we'll look at U intersected with A, but observe that that is a subset of U intersected with A bar, given that A is a subset of A bar. But now let's observe the following. And that is that U intersected with A bar is most definitely the empty set, because what we're doing there is intersecting a set and its complement. But anytime you intersect a set and its complement, well, you got to get the empty set. So what did we just find here? Well, notice that we found a neighborhood of X. U is that neighborhood of X that does not intersect A. But observe that that is not this statement. So we have proven this reverse direction using the contrapositive. Okay, so now let's prove this forward direction using the contrapositive. So notice the right-hand statement says that every neighborhood of X intersects A. So the negation of that would be there exists a neighborhood of X that does not intersect A. So let's take that neighborhood. So take a neighborhood, and we'll call it U of X, such that U intersected with A is the empty set. So again, the ability to do that is given by the negation of that every neighborhood statement up there. Okay, great. But if U intersect A is the empty set, that tells us what? Well, that tells us that A is contained in X minus U. Okay, but if A is contained in X minus U, well, we found a closed set containing A. So I'll just put here, this is a closed set because it's the complement of an open set. Okay, but let's notice that X is not inside of X minus U. And how do we know that? Well, notice that U is a neighborhood of X, meaning that X is inside of U. But if X is inside of U, then X is not in its complement. Okay, but observe that we've got a closed set containing A, but any closed set containing A is a subset of the closure of A by our definition over here. So observe that we have X is not an element of X minus U, but again, this X minus U is a subset of the closure of A. But then we see that X is not an element of the closure of A, which is where we needed to end up for this forward direction being proved by the contrapositive. Now let's look at an example that really shows us that the definitions are acting the way that we want them to. In other words, they're producing results that kind of make sense. So let's take a set A to be the half open interval from 0 to 1, including 1 but not including 0. And so I think we can all agree that the closure of this should be the set 0 to 1, let's see, including both 0 and 1, so that closed interval. Okay, so let's prove this, perhaps not the most efficient way, but we'll prove it using some techniques that I think will have a nice carryover. And so let's observe that A is always a subset of its closure. By the definition of its closure, that means that the half open interval from 0 to 1, not including 0, is a subset of A closure. So that gets us off to the right point. Now we'll show that 0 is also in the closure of A. But we'll use the result that we just proved, and that is that every neighborhood of 0 will intersect A. So let's take U, a neighborhood of 0. So in other words, U is an open set containing 0. But let's recall, in the standard topology on R, we know what that means. And that means the following. There exists a number delta bigger than 0 such that the interval minus delta to delta is contained inside of U. But now let's note the following, and this will finish this whole first claim off. And that is that if we look at delta over 2, that's going to be on the interval from minus delta to delta. And it's on the half open interval from 0 to 1 because it's bigger than 0. And I guess I should make the point that it's less than 1. We could encode that here, but generally we think of delta to be a small number. Okay, but now let's observe that this is inside of U intersect A, proving that U and A have a non-trivial intersection. But then since U was taken to be an arbitrary neighborhood, well, that's exactly what we needed to end up proving to show that 0 is inside of the closure of A using that previous theorem. Okay, so observe that what we have done so far with these first 2 points is we have proven that the closed interval from 0 to 1 is a subset of the closure of A. Now we need to show that it is the entire closure of A. So what we'll do is take things outside of that closed interval and show that they cannot be in the closure. And we'll show that they cannot be in the closure by showing that they don't satisfy that previous theorem. Okay, so let's say that we've got something to the left of that interval from 0 to 1. In other words, we have an x less than 0. And then what we'll do is construct a neighborhood of this x that does not intersect A. But that's actually pretty straightforward. Notice that minus infinity to x over 2, well, notice that's a neighborhood of x. And I think that's pretty straightforward to see that that is a neighborhood of x. But it does not intersect our set A, which is the set from 0 to 1. So in other words, this is the empty set. So in other words, we found a neighborhood of A that does not... So in other words, we found a neighborhood of x that does not intersect A. But that's exactly what we needed for x to not be in a closure. And then I guess we could do something really, really similar for the things to the right of 1. So if x is to the right of 1, in other words, it's bigger than 1, then that means that x is equal to y plus 1 with y bigger than 0. That's straightforward to see. But then let's observe the following, and that is that x is in the following interval, and that is y over 2 plus 1 to infinity. But there's a neighborhood that contains x, but let's observe that this neighborhood that contains x does not intersect our half open interval from 0 to 1. So let's take this off because we did that intersection. So in other words, what we just constructed was a neighborhood containing x that does not intersect A, but that means that this x is also not in a complement. Sorry, not a complement, a closure. So, well, what does that mean? Well, notice that we've got the closed interval from 0 to 1 is a subset of a closure, but then anything outside of that closed interval is not inside of a closure. But putting these two things together is exactly showing that a closure is the closed interval from 0 to 1. Now, I guess before we really move on, we should look at some pictures here. So let's look at a picture for this first bit where we're showing that 0 is inside of a closure. So let's maybe put 0 here and we'll put 1 here. And our set A would be this yellow shaded stuff like this. But notice that this minus delta to delta is like this kind of interval right here. And then what we're doing is we're picking out this delta over 2, which kind of clearly lives right there. Okay, nice. And then, well, we could make similar pictures for the rest of this, but they involve something like having our point 0 and let's see, and being able to like put a little bubble around anything to the left of 0 that does not contain 0. And you could draw a picture for the other one too, but I'll maybe leave that for you if you need that. Okay, so here's how we'll define the notion of a limit point. So given a set A of x, we say that x, little x, is a limit point of A if every neighborhood of x intersects A at a point other than x. So this is kind of a tweak on that theorem that classified points from a closure. It just kind of maybe singles out special points inside of a closure, if you will. And so notice that we could write that as follows. For all open sets U, where x is in U, if we take U intersected with A minus the singleton x, we get a non-empty set. So this is what it takes for x to be a limit point of A. And let's denote A prime to be the set of all limit points of A. Now let's look at some definitions. So let's observe in the half open interval 0 to 1, not including 0, 0 is a limit point. And in fact, we essentially proved that in the previous example. And also, every element of the set from 0 to 1 is also a limit point of the set from 0 to 1. We won't prove that carefully, but I think that's pretty straightforward. Now let's observe that the set of the integers inside of the real numbers does not have any limit points. And we can show this pretty easily. So let's take any n within the integers and let's note the following. And that is that the open interval from minus n over 2 to n over 2 intersected with the integers minus the singleton n is most definitely empty. Now that just shows that no integers are limit points, but observe up here that limit points don't have to come from the set. They could come from outside of the set. So we would also need to show that no non-integers are limit points either. So how could we do that? So if x is not an integer, then let's observe that x is on the following open interval, maybe from the floor of x to the ceiling of x. So like the greatest integer function and the least integer function. But let's notice that this is a neighborhood containing x. I think that pretty clearly contains x. But let's notice that this neighborhood does not intersect the integers at all. So there what we did is we found a neighborhood of x that doesn't overlap with the integers at all. Needless to say, the integers minus x. Well, I guess the integers minus x is just the integers in this case. Okay, so anyway, that kind of clears up this whole thing right here where z has no limit points. Now for our next example, let's take all of the reciprocals of natural numbers. And so that would be everything of the form 1 over n, where n is a natural number. So that's like ... 1 over 5, 1 over 4, 1 over 3, 1 over 2, and then 1, or 1 over 1. And I want to claim that 0 is the only limit point of this set. And let's first show that 0 is a limit point. And so let's take u, which is open in x, so that 0 is contained in u. So in other words, u is an open neighborhood of 0. But then observe that that means that there exists a delta bigger than 0 such that the open interval from minus delta to delta is contained in u by the definition of an open set in R. Now, next up, what we want to do is find some natural number n such that 1 over n is less than delta. We can always do this. And now let's notice that 1 over n, since it's less than delta and it's pretty clearly bigger than 0, that means it's on the interval from minus delta to delta, which is a subset of u. And so, well, notice that tells us what? That tells us that 1 over n is inside of u intersected with a. But I guess a minus 0 and a are the same here, since a does not contain 0. But I guess that's the condition that we needed for 0 to be a limit point. Now let's see what else we have to prove. So maybe what else we have to prove is that no member of a is a limit point. And so to do that, what we'll do is take 1 over n inside of a, and let's note that the following open interval is an open neighborhood of 1 over n, and that's 1 over n plus 1 to 1 over n minus 1. So again, that's a neighborhood of 1 over n. But then when we intersect that with a minus 1 over n, we get the empty set. So what we did is we found an open interval, in other words, a neighborhood of 1 over n that does not intersect a in a place other than itself. But that means that 1 over n cannot be a limit point. And then maybe as a little bit of a homework exercise, I'll let you show that nothing else inside of the interval from 0 to 1 is a limit point of this set. All right, so next up, let's prove a nice result that ties together the notion of closure and the notion of a limit point. All right, so let's now show that the closure of A is simply A unioned with its limit point. So this is a nice result. And we're going to do this with double set inclusion. So in other words, we're going to show the left-hand side is a subset of the right-hand side and vice versa. So let's start by showing that the closure of A is a subset of A union the limit points of A. Okay, so let's suppose that X is in the closure of A, so that's A bar. And then let's break this into two cases. So I'll call them case 1 and case 2. So the first case is, well, what happens if X is in A itself? Well, let's notice if X is in A itself, well, A itself is definitely a subset of A unioned with its limit point. So there's really nothing to do there. And so the second case is the interesting case, which is if X is not inside of A. Okay. So now let's take a neighborhood of X and we'll call that neighborhood U. But notice that since X is in A closure, that means that the intersection of U with A is non-empty. So we've got the empty set is not equal to the intersection of U with A. Okay, but then since the intersection of U with A, but now the intersection of U with A is going to be the same thing as the intersection of U with A minus the singleton X. And that's because X is not an element of A. But this object right here, not being the empty set, is exactly what we need for x to be inside of the set of limit points. But then the set of limit points is a subset of A unioned with the set of limit points. So either way you get at it, you have x is an element of A union limit points of A. Okay, so now let's look at this reverse containment. So let's suppose that x is inside of A union A prime. Now, we're going to break this into two cases again, and they're going to almost be the same case, or the same as the ones that we just saw. So let's say case 1 would be the case if x is inside of A. But notice that A is a subset of A prime, so we're done there. So the next one will be x is not an element of A. But if x is not an element of A, but it's inside of A union the limit points of A, that means that x is an element of the limit points of A. Okay, but then we'll take an arbitrary neighborhood u of x, and since x is a limit point, that means we know that u intersected with A minus x is not the empty set. But then, since x is not in A, the intersection of u with this set is the same thing as the intersection of u with A itself. But then, let's see, the intersection of u with A being not the empty set is exactly what we need for x to be in the closure of A. And that finishes off this second containment, finishing the proof. Okay, so now let's look at an example, and then I'll leave you with some exercises. Okay, so for our example, let's take x to be a 5-element set. We'll name those elements A, B, C, D, E. And then we'll define the following topology on this set. So the open sets will be, well, the empty set and everything, the singleton A, the doubleton CD, this set with elements A, C, D, and then a set with elements B, C, D, E. But if those are the open sets, we can pretty easily calculate the closed sets by looking at all of their complements. So that would be nothing, everything, B, C, D, E, A, B, E, B, E, and A. Now let's find the closure of a couple of sets. Let's first find the closure of the singleton B. And let's use the definition that we had at the beginning of the video. Remember, the closure is the intersection of all closed sets containing this set. So let's see, that's going to be B, C, D, E, because that's a closed set containing this, intersected with A, B, E, there's a closed set containing this set, intersected with B, E. Again, that's the last closed set containing this set. But if we perform that intersection, we're going to get B, E. And there you have it. That's the closure of the singleton B. And now let's calculate the closure of AC, but notice that that's going to be AC unioned with the limit points of this. And so that's going to be AC unioned with, now let's write down the limit points. So I claim that B is a limit point, and that's because every neighborhood of B, there's only one neighborhood of B here, so it intersects our set in a place other than B. It intersects our set in C. So that means that B is a limit point. And then, well, we don't need to check if C is a limit point because C is already in the set. And since we're looking for the closure, we don't really need to know if or if it's not a limit point. Let's go on and move to E. No, D. So let's look at the neighborhoods of D. So that would be this thing right here, that's a neighborhood of D. This is a neighborhood of D, and this other one is a neighborhood of D. And notice that they all intersect our original set, meaning that D is also a limit point. Now let's do one more. We've got one more point to look at, and that would be E. And observe that we've got a single neighborhood of E, and that's this open set B, C, D, E. That intersects non-trivially with our original set, meaning that E is also a limit point. Putting this all together, notice that everything, in other words, the entire topological space, is in fact the closure of this AC. Okay, so now I'll leave you with some exercises. All right, here's some exercises for you. The first one starts with the same setup that we had in the previous example, but now let's find the limit points of these three sets. The singleton A, the two element subset B and C, and the three element subset A, C, D. So next up, let's do that exercise that I mentioned during this example or a previous example. Let's say A is the reciprocal of all natural numbers, the set of the reciprocal of all natural numbers. Let's show that if x is an element of the open interval 0 to 1, then x is not a limit point of A. Then let's give Z the finite closed topology. Let's recall that that means that all finite sets are closed and all closed sets are finite, except for everything, I guess I should say. So here we'll say that U is open if the complement of Z minus U is finite. And of course, not written here is the fact that the whole set is both open and closed. And so our goal here is to find the limit points of the set containing 1, 2, and 3, and then the set of all even integers. Finally, let's show that the closure of the open interval from A to B is in fact the closed interval from A to B, which is maybe definitely something that we should expect. And that's a good place to stop.